Now we are going to apply the loads. As you can see here, first load is self-weight. It's automatically applied in the model. You don't have to do anything in it. Second one is furniture. Furniture loads is actually the loads that comes from handrails, walkways, access platforms, and other loads such as electrical, lighting, signage. So summing it all up, I'll be adding a generous of 4 kilonewton per meter on top of the wall. You can select this icon over here to apply a linear or uniform distributed load. Hit surface and choose this icon over here where you can specify a linear loads on top of a surface. Direction will be Z and it's going to be -4 kilonewton per meter. The negative sign denotes downward. Add, and then you don't have to apply on the entire element of the wall, but rather choose just the top of it, and it will give you this object selection. And then choose edge 4 and click OK. Now you can see here the loads. If this symbol of loads is not showing on your screen, all you have to do is right click your mouse, go to display, go to loads, and click all this icon over here if they are unchecked. Okay. Next load will be earth pressure dry. For the earth pressure dry, it's a combination of lateral loads, usually in a triangular pressure or uniformly varying load on the wall, plus a uniformly distributed pressure on the surrounding perimeter base. That's actually the weight of soil. If it's saturated, then it's just the gamma effective multiplied by the depth. For this time, we're considering earth pressure dry. So we're just going to be considering a bulk unit weight. For example, it's very conservative. Usually it should be gamma dry only, but I'll be considering gamma bulk. Okay. For this one, to be able to apply the uniformly varying pressure load on the wall, all you have to select is go to the same icon over here and then hit or go to surface, and then if you see this hydrostatic pressure in here, usually this is intended for water only, but it gives you the flexibility to also use for soil. Click this one and it will give you this option over here. So it's asking a pressure. This pressure will be 0 because we don't have we will not be starting on a uniformly pressure load on the wall, but rather a uniformly varying load. So it's going to be 0. Right. For this one, it's asking the unit weight of the liquid. Take note that the unit should be in kilogram per cubic meter. So a 20 kilonewton per cubic meter bulk unit weight of soil will be converted to -2040. Note that the sign there is actually later on you will see the effect of sign if I apply the loads. So basically it's a trial and error. If you put positive in here and if your pressure goes inside the wall, which is quite the opposite because our soil is actually around the perimeter, then you have to reverse the sign. So it depends on the orientation of your wall, sort of local axis. And then this liquid height over here. Okay, you have to specify until what level is the soil or the backfill around that area. So it depends on where did you put your 0, okay, 0 Z point, right? So it depends on your elevation. For this one, we will specify 1 meter because if I go front, this is my 0 elevation, as you can see there, that here you can see the coordinates here. If I put at 0 at 3, you will find that this is at Z0. All right, so this is my Z0. This will go negative if I go down. This will go positive if I go up. So that's why the level of soil at the perimeter of the PST is 1 meter. Okay, it will be backfilled by 1 meter. So I said 1 meter in here, and choose this value over here, or just this direction over here, because it's going up. Choose this value if it's the opposite or the other way around, and then click add, and then you apply on this wall. Okay, and then it should be there already. So you see here that the pressure is already been applied in here. Just ignore the sign over there because this is a cylindrical kind of application of loads. So somehow you will see some sort of this symbol in there, but it's not actually showing for this cross section. It goes the other way around. That's why it seems like there's an excess over there, but actually there is not. All right. So this is the way how you apply the loads. Now you can see it's negative 20.01. It means the kilogram per cubic meter has already been converted to kilonewton. All right, so after that, the next one will be you need to apply the uniformly pressure load on the base due to the bulk unit weight of the soil. So you go over here again, same icon, and then you go to surface and choose this icon over here, which is uniform planar load, right? And then you specify here the pressure. So the question now is, what's the pressure that we are going to apply in here? Of course, you've got the unit weight 20 kilonewton per cubic meter multiplied by a height of 1 meter. So that's 20 kilopascals. I hope that's pretty much straightforward without showing you the calculation. All right. And take note that you always need to apply negative here. It denotes a sign of downward. And then click this icon over here. Again, since this is the geometry has been made using polyline, you have to be really careful how you apply the loads. For this one, it should be side 4. As you can see here, it's already applied at the perimeter of the base. That's for the earth pressure dry. Now we go to earth pressure wet. Okay, for it's similarly, it's done as the earth pressure dry, but here it's quite a bit tricky because for the backfill of 1 meter, we assumed that the level of water rise up to the ground level. So the soil around this PST is going to be fully saturated. And when it's fully saturated, you know, the buoyancy force is actually acting already. It means that we're not going to be using the bulk or the saturated, but rather we're going to use the effective unit weight. What's effective unit weight? It's basically the difference between the gamma saturated less water, because you have to deduct the buoyancy force in there, right? So we go the same icon over here, and then we go to surface, and then we will be using again this option over here for hydrostatic force, right? And okay, there's no initial pressure, but we will be changing this unit weight to the effective unit weight. What is the effective unit weight? It's basically 2040 as the bulk unit weight, or let's just use a gamma saturated, all right? Gamma saturated of soil, let's just say 18 kilonewton per cubic meter. All right, what is 18 kilonewton per cubic meter? I will hit my calculator here in kilogram. Times 9.80, 18 divided by 9.81. So that's around 1,835 kilogram per cubic meter. So 18 kilonewton per cubic meter is 1,835 kilogram per cubic meter. I just converted it. Less, we have to deduct the unit weight of water, which is 1,000. So what's left is only negative 835. Oh, that's correct in there. Negative 835 kilogram per cubic meter, right? So don't be confused of this. This is the effective unit weight, or gamma effective. That's basically the gamma sat less the density of the water, which is 1000. Negative 1835 less 1000. That's negative 835 kilogram per cubic meter. All right. And I think that's pretty much all what you need to do in here on the earth pressure wet. You have the same height in here and you have the same direction. All you just need to do is add it and then select this surface over here. Now you see it's already been applied in there. Let's go over there. Okay. Again, that one goes to the other side. I don't know why it's showing like that, but actually you can verify it later on. That's correct. All right. So next up, we are going to apply a pressure load at the base. And how to do that? It's basically this symbol over here. And now this one will change because we're using gamma effective also for the pressure at the base of this perimeter, perimeter concrete of PST. So the height is 1 meter and the gamma effective will be 18 kilonewton per cubic meter less 9.18, or let's just say 10 for the density of water, 10 kilonewton per cubic meter. All right, so 18 less 10, so that's 8 multiplied by 1 meter of height. So that's what going to be 8 kilopascals applied at the perimeter of the water tank. Okay, you just have to select this item over here again and choose side forward, and that's it. That's pretty much how to apply uniformly varying load and pressure load on the lateral element, and of course the perimeter base, right? Then next up, we've done already with earth pressure dry, earth pressure wet is the searcher's loads. Now for the searcher's load, normally we would assume a heavy searcher's load at the perimeter of the base to be on the conservative side. We go on the surface again and we choose the same icon for uniform loads, and we will be putting here 12 kilopascals for a heavy weight at the perimeter. Okay, this is for the live loads. This will be for either people working around on this area or some other type of live loads. So negative 12 kilopascal, add and choose this icon here again and select side 4, right? And then close. And then we go to the hydrostatic. Now this is quite a bit complicated, I would say, but it can be followed, to be honest. So for this one, what we have to do is we need to apply a hydrostatic pressure on the wall due to the presence of the water surrounding this PST. Okay, first up, we need to go to the same icon over here, and then we go to surface, and then this icon over here. So what's the unit weight of the liquid? Of course, since it's hydrostatic, so it's just negative, you can guess it, the density of water. And then for the height, it's going to be 1 on this area. Okay, and I think that's pretty much all. Add. All right, as you can see there, it's already been applied. And then on the base, we need, all right, so this hydrostatic pressure isn't just apply on this wall because we also have a hopper over there, right? So it has to be applied also here. The same item. I should have applied both, but now I'm going to create another one again. It's still the same, negative 1000 by 1, and then just choose this element over here. I think it's already applied. Okay, just hit add first and then select that area over there and then just choose side 2. Okay, there you have it. So as you can see here, there is like a termination over here, which is the pressure is not yet 0 due to the height. Due to the height because it's starting from 1 meter above the base or above zero. So this is a correct diagram. Now there is also a pressure or no uplift, loads on this perimeter, on this base of the tank, and on the base of the hopper. That's the next loads that we are going to apply. How do we apply that one? By simply choosing this uniform planar load. Okay, for the uniform planar load, let's say that the height of the water here is 1 meter, right? So it's just, you guess it, the load will be 1 meter multiplied by 10. Usually it's 9.81. Let's just go to 10. So that's negative 10. Or of course, it's an uplift pressure, so the direction will be reverse. So it's 10 kilopascal. And then, okay, don't forget to add first and then hit this area over here and choose side 4. Now you can see the uplift pressure is going upward. So that's correct. And also this one over here is a sloping slab, sloping base. So how do we do it? We go first on the cross section so that I can show it to you. Those heights, right? As you can see, this height over here from this area to that area, I hope I can show it to you using dimension line. So that's around 0.76, right? 0.76. Or you can say 0.8. All right. To be on the conservative side, I will be choosing, you can also go for average, but I'll be choosing the lowest point, okay? Just to get the maximum uniformly applied uplift pressure at the base of the water tank. So if this is, for example, 0.76, 0.8, roughly 0.8 plus 1 meter over there. So the total height of the uplift, pressure now is 1.8. So 1.8 multiplied by 10, definitely 10. That's the uplift pressure at the base of this slab over here. Okay, so how do we do it? Go here and then choose surface and this area over here. Now this is going to be 18. Understood? Because of the submerged water. So 1 meter there, just to double check. 1 meter here plus 0.76 here. So that's 1.8 multiplied by 10. So that's 18. Correct. All right. Okay, if I have some error on the calculations, just comment down below or just ignore it and correct it in your own calculations as well. And then hit the area where you need to apply the loads. This item over here. And it should be polyline side 3. Let's see if it's going to be applied on the correct one. That's it. So as you can see here, it's already been applied at the base. It has already been applied at the base. Okay, so we have an uplift pressure at the largest, part of the PST, but we don't have uplift pressure at the base of the hopper yet. So that's something that we need to apply as well. Again, we will be measuring. Let's use this tool, which is very useful. You're measuring dimensions, or you just go to tools and then dimension lines, and then hit wherever you want to measure. This is 1.76. So this is around 1.76 plus 1 is 2.76 multiplied by 10. So that's 28 kilopascals. All right, 28 kilopascals. That's applied at the base of the hopper. Okay, So we go to planar loads again, and then instead of 18, let's apply 28 here, add, and then, okay, how do you revolve this? You just click Control, and then your roller on your mouse. No, roller. I think, sorry, it should be Shift, and then your roller. Hit your roller in the mouse, and then hit this icon over here, and then choose polyline. All right, there you have it. So now the uplift pressure has already been applied on the base of the slab or on the surface where water is exposed. This is the case where the groundwater level reaches up to the ground level or at the top of the backfill area. Okay, but you have to verify that it's not usually happen like that. So there's certain levels where the groundwater level actually rise into its maximum level. Okay, so that's for the hydrostatic. Of course, what's missing is our sludge or our water. Now this is quite a bit of a gray area whether how do we apply. Is it a sludge or is it basically a water? Well, the good thing is the unit weight of sludge and the unit weight of water is very near. So whether it is sludge or water, it doesn't matter. All right, so what I'm going to do is I will apply water on this very huge part of the PST, and on the upper part where it actually collects sludge, I'll be applying a sludge density. Okay, if that makes sense. So with that, I will be choosing again this value over here, which is basically water. So as you can see now, it's water, but I will change this sign because the pressure is now coming from the inside. So it depends on the orientation of or the local axis of your elements. I will choose 1000 here. And I will now choose the liquid level. I'll bring it up until 2 meters, which is exactly the height of the wall. I'll just say it reaches its maximum level, although there's an what do you call this, freeboard. It's basically the distance between the maximum level of the tank and the maximum level of water. Freeboard of around 300 mil. I'll just say 2 meters to be on the conservative side. Okay, and I will select this area over here. But before doing that, it's very important that you need to change this to the correct type of loads that you're applying. This is water or sludge. And I will hit the wall. But before that, don't forget to add, and then I will hit the wall over here. So there you have it. You can see here a uniformly varying load inside the wall, right? And also, aside from the uniformly pressure on the wall due to water, we also have a loads, of course, on the slab, right? So how do we do that? It's basically a planar load, and the height is 2 meters, so definitely you know it already. 2 meters multiplied by 10, so that's around negative 20 kilopascals on the water. Correct. Okay, so all right, so this is quite a bit tricky. It's negative 20 on this area at the surrounding perimeter, right? But as you go down, this is sloping of 0.76, correct? So if I'll say negative 20, it will be less conservative, you know, because I'm just considering the perimeter of the PST. But if I go on this area and choosing the maximum depth, so that's around 0.76 as we measured previously. So that's around 2.76 or roughly 2.8. So 2.8 multiplied by 10. So I will be changing this to negative 28, if that makes sense too. All right, so you click the base and choose side 3, and there you have it, the pressure due to the water. And now our last we will be focusing on last application of loads. We will be focusing on this upper area. So I'll just select this upper area. We can select it because it's again, a polyline. I have a suggestion. When you do the polyline to create the geometry, make sure that you do the polyline one by one so that this element will be separated from this element, and from the wall element. That's how you do it properly, so that they will be separated. Because I started it as a polyline, continuous polyline on that area. Now they are one element, but actually there is a way to select them, but it's quite a bit tricky and makes you, it gives you difficulty in applying loads, applying properties, etc. All right, so when you do it, you create the polyline over here, right? That's how we created the geometry in this polyline, for example. And then now geometry, right? So you're creating one by one. If you create from this point to this point and then click apply, right? Don't continue from here and then from there to the last point. You just click this one here and then go up, finish it, apply, and then create another polyline so that these elements will be separated. Okay, going back, we are now going to apply loads on the upper area. Okay, for the upper area, we will be applying quite a bit complicated. How are we going to apply pressure at the base? Normally, there's like a mass of concrete, sloping mass of concrete over here. But to simplify this complicated geometry of the hopper, I'll be just applying a, let's just say, conservative pressure at the base. Okay, how? I will go here and go to surface and uniform pressure. How much pressure should apply at the base? Well, previously we've shown, we go to the, okay, I'll just be measuring something in here for you to be able to understand the application of loads. So from here to here, this is basically 2.76. All right, I'll just say that from 2.76 it contains water. All right, so that's 2.76 multiplied by 10. And then from this height to this height, it contains like almost a solid particle sludge. And as you all know, the sludge density varies from somewhere an average value of 11.5 kilonewton per cubic meter. So I'll be applying now 2.76 multiplied by 10, that's the density of water, plus this area over here, which is 1 meter. 1 meter multiplied by 11.5. So that's around 39.10. So 2.76 multiplied by 10, and then 0.71 here because that's 0.76. So that's around 39.10. I'll just conservatively apply, it's usually 40 kilopascal. I will just apply conservatively 50 kilopascals, all right? To be on the conservative side, 50 kilopascals pressure at the base. Hit this area over here and choose -15. Add and choose this area over here. And also, sorry, just hit the base here and choose side 4. Okay, there you have it. You're seeing a 50 kilopascals applied on the base due to the presence of some sludge particles and combination of water and sludge, right? And then sometimes they put some mass of concrete also here in a slope form. That's why I've increased it from 40 kilopascals to 50 kilopascals. So take into account those, you know, geometry, right? 50 kilopascals. Okay. Now we are going also to apply some uniformly varying pressure on this wall to be on the conservative side again. But in reality, it's like the presence of the sloping mass of concrete in here will basically reduce the applied pressure on the lateral part of this hopper over here. But still, we are going to apply Okay, so similarly, the density of water is 1000. We are going to apply it inside, so the sign should be positive. And then the level of water here will be changed, right? So when you apply a pressure, it's 2 meter from here, and now the liquid level height will be different. So it goes up in there, but our reference here is, yeah, our reference here is different because our reference is always the 0 one. So you don't have to change this one. When you apply it in there, it will automatically get the level of this base. So when you click this item over here, or add first, and click this item over here, it's not selecting, but we'll try our very best. Ooh, sometimes you encounter this type of these challenges of applying loads when you model your geometry. Oops, it's 3. No. Okay, when you accidentally apply some loads and you think that it is not correct, all you just have to do is go to loads and then load table, and then from there, because if it's not showing correctly in there, you have to go in here and see if there are some applied loads that's not necessarily needed. So as you can see here, this is the last loads that we have applied, and this is the loads. So definitely it's not applied yet. So there's no loads applied on the hopper yet. So you go over again, and you go to surface, hydrostatic. This is the last load that we've applied. All right, click add. I always have that kind of mistake. Yeah, there you have it. Select side 2. Okay, so there it's already applied. Okay, the pressure on the hopper. Okay, so that's that's actually how to apply loads, and I believe that's the loads that that's the last loads that we are going to apply. If you have some wind loads, which is also applicable on this type of structure, you can also apply it. But for the meantime, for simplicity, we will be omitting wind loads because it will be just exposed 1 meter above ground, right? So that's how we apply loads. And next up, we will be proceeding for the analysis and checking of the structure.